Hello, and welcome to the Electric Classroom. My name is Tom Sullivan. In this Powering Your Head series tutorial entitled Understanding Power in DC Circuits, I'll try to shed some light on power and work in DC circuits, discuss their calculations, and use a common waterfall analogy to hopefully make it all more brain-friendly. Power is defined as the rate of doing work and is related to work by time. As you can see in the equation shown here, power represents a certain amount of work in a certain period of time. By this definition, work is expressed in joules, time in seconds, and the power measurement for P is in watts. And that makes watts equivalent to joules per second. A joule, by the way, is a small amount of work, roughly equal to the energy you'd expend picking up an apple from a table. Work is defined as the accomplishment of motion against the action of a force which tends to oppose that motion. For our purposes, work and energy are considered numerically equivalent, although the term energy is most often used more generally to include the capacity to do work. Work is being done when electricity is generated, as well as when it's being consumed. And a point I'd like to make pointedly here is that work is an amount of energy, whereas power is a rate of energy usage or production. To honor James Watt, we use the term watts instead of joules per second, but please remember it's a rate, not an amount. As you can see in this rearrangement of the equation here, power, which is the rate of doing work, times T, the amount of time that rate of work is performed, yields the amount of work done, or the amount of energy produced or consumed. This is really just like multiplying your driving speed in miles per hour times the length of time that you drove to yield the distance that you traveled. A rate times time is an amount. Now, in our electrical business, the rate of doing work is measured in watts, and the amount of work done or energy consumed is measured in watt hours, or more commonly, kilowatt hours, or at the system level, megawatt hours. This is used because watt seconds is simply too small a measure. Residential customers pay the power company for the energy they consume or the work their electricity has performed for them each month. In our simplified example here, the customer has they've had their 100 watt light bulb on for 10 hours this month, and therefore they have to pay for 1,000 watt hours, which is equal to 1 kilowatt hour. Now, here's a simple schematic and graph of a resistive DC circuit. On our graph, the x-axis represents time, with 0 being the point that will start monitoring the circuit's output, and the elapsed time from that 0 point will move to the right. The y-axis is marked with only one scale, but we'll use it to measure all three magnitudes of interest to us. In this case, amps, volts, and watts. And as you can see from the schematic, the supplied voltage is 3 volts. The load is drawing 2 amps. So the power computed as volts times amps, or 3 times 2, is 6 watts. Now, please notice in a DC circuit, all 3 of those quantities are constant. Therefore, their graphs are a straight line. So to pick on volts, at any point in time, starting at our 0 point and following our elapsed time, the voltage from the battery is a constant 3 volts. The resistor is fixed, so our amperage draw is a constant 2. And because of that, when we multiply the 2 together, we'll get a constant 6 watts. Now, on this slide, I've marked the 1 hour position along the timeline. And I've highlighted the area under the curve between the, bounded by the power line of 6 watts and the 1 hour mark. Because that represents the energy consumed or the work done by the resistor in that period of time. Remember, watts times time is the amount of work done or energy consumed by the circuit in that time. It's very similar to measuring the rectangular throw rug in your living room that, let's say, is 8 feet by 10 feet. So 8 by 10 gives you 80 square feet. But in our case, one side is 6 watts, the other side is 1 hour. So the product, represented by this shaded area under the power line and bounded by the 1 hour mark, is the amount of energy consumed by this circuit in that time period. In this case, 6 watt hours. And as we'll see when we do our next video, even though AC circuits are slightly more complicated because they're not constant, this basic idea will still hold true, that the work performed or energy consumed is the area under the curve for a particular amount of time. In DC, it happens to be a straight line. In AC, it's going to be a curve. Alright, so now that I've announced to you that volts times amps is watts, let's take a moment to analyze just how that comes about using an analogy to apply some interpretation and try to gain some understanding of these quantities. To do this, we'll use one of the most commonly used analogies for electric voltage and current, and that's a waterfall. here's the waterfall. Here's my interpretation of that as a drawing. Now the height of the waterfall above ground, which determines the supplied water pressure as the water falls, that's analogous to the potential difference between the 2 points of the source's output. And the water flow over the waterfall is analogous to the flow of electrons in the circuit. And for those of you who care, I'll just mention that my arrow, which I've drawn to match the flow of the water on the waterfall, is actually demonstrating what we refer to as conventional current. Now the power delivered by the waterfall at the bottom of the waterfall is the product of these two quantities, the height of the waterfall and the flow over the waterfall. Just as the voltage output of the source times the current flow in the circuit defines the electric power in this circuit, V times I. And if we put a water wheel at the base of the circuit, or at the base of the waterfall, we'd find the power we could get from it would be proportional to the product of the height of the falls times the flow of the amount of water coming over the falls. And the amount of work we could get out of that would be that power times the length of time that we allowed the water to flow and turn the wheel, using the definitions that we've already covered. Now, at this point, hopefully everything I've said so far seems perfectly reasonable, but I've got to mention that I never really have substantiated my claim that P equals V times I, except for my analogy. So, for a slightly more technically complete explanation, let's look at the formulas associated with the definitions of these quantities, and we'll see how it all comes out on paper. We'll start by defining volts and amps, and then combine those formulas with our power formula, and see how we do. The definition of 1 volt, it's defined as the potential difference between 2 points when the amount of work required to move 1 coulomb of electric charge from one point to the other is 1 joule. So it's an amount of work per charge. And from this definition, we'll solve for W, because we're going to use that in just a minute. As far as the ampere is concerned, it is defined as the rate of flow of electric current through a point in a circuit when 1 coulomb of electric charge passes that point in 1 second. So it's an amount of charge per unit of time. And from this definition, we'll solve for T. All right, now to put these all together, we'll start with our definition of work. It's equal to power times time. We'll solve for power, so it's work divided by time. And then next, using our rearranged formulas, we'll substitute QV for W and Q divided by I for T, And you can see, if you cancel and invert, this reduces to power is equal to volts times amps. And let me mention at this point too, you can see now P is equal to V times I, so P is directly proportional to both quantities. Increasing either or both would increase the power, just as raising the height of the waterfall or increasing the waterfall's flow would increase its power. Now, I'd be remiss at this point not to mention some other formulas, and I'll use the power wheel to demonstrate that. If it's new to you, I suggest you give it a look. I've found it pretty handy over the years. Basically, the power wheel takes Ohm's law and the power formula that we just derived, and it mixes them together in every combination to give you an easy reference to use. For each of the four quantities, P, V, I, and R, 3 different formulas are given for each one. And those formulas use all the other quantities. So, for example, if you want to find P and you happen to know R and I, your current and resistance, you just look at the 3 formulas and you see which one has both of the quantities that you know, and you know now you can use I squared R. And what it does for you is very often it'll save you having to use 2 formulas because it's already combined them for you. Now, the other thing about it is that it can be an analytical tool for you sometimes. As an example, let's say we want to know which light bulb has the smaller resistance, a 40-watt bulb or a 100-watt bulb. Well, we could look at the 3 formulas available to us for power, because it's watts we're concerned with. We know that the voltage of the 3 light bulbs, of the 2 light bulbs, are the same, 120 volts, right? So that won't matter, and we're left with P is equal to V squared over R, but the important part is the R is inversely proportional to the P, meaning the larger the wattage, the smaller the resistance. So we've rather handily answered our question. All right then, to summarize, for DC circuits, power is constant because the voltages and currents are constant. And this makes both the concepts and the formulas rather straightforward. And although, as we saw on the power wheel, there are a few formulas that we can use for it, we use P equals voltage times current for 2 reasons. One is it's very commonly used, but secondly, it aligns itself so well with our waterfall analogy. Remember that power in watts, which is joules per second, is a rate of generation or usage. And work is the amount of energy in kilowatt hours produced or consumed over some period of time at that rate. Graphically, that work is represented by the area under the power line, or in AC it'll be a curve. And this is the product of the time times the power. I hope you've enjoyed this tutorial. I invite you to come back in 6 or 8 weeks when I hope to have my next offering for you, which will be entitled Real Power in Single Phase AC Circuits. And lastly, I want to give a shout out to Aaron for helping me with some of the graphics on this video. See you soon.